See, yesterday we have seen the ability of a Brewster plate to replace a dichroic mirror in the operation of an optically pumped gas laser to provide much reliable performance of such a laser when pumped by another laser. Let me very briefly again go through as to how does it work. You know very well that reflection of light not only depends on the angle of incidence but also on the polarization of light. So what actually I mean is that suppose light shines on, let us assume, a rectangular glass plate. So as you know, part of light will be reflected, another part will be transmitted. Now this reflection of light, or as well as transmission of light, not only depends on the angle of incidence, but also on the polarization of this incident. The dependence actually is schematic, is represented in this. As you can see, at an angle of incidence, which is called Brewster angle of incidence, the reflectivity of the p-polarized light is that polarization which is contained in the incident plane. Incident plane basically is the plane that contains the incident light and the normal to the incident surface. So this is the normal, this is the incident light. So this plane of paper is the incident plane. So the polarization which lies on this plane is this polarization is called p polarization. And the polarization which is perpendicular to this plane is called S polarization. So for p polarization, the reflectivity at Brewster angle of incidence is 0. That means p polarization cannot be reflected for this Brewster. This actually depends on the refractive index of this medium. However, the orthogonal polarization, that is the S polarization, which is perpendicular to the incident plane, can be both reflected as well as transmitted. So this is the reflection and rest will be transmitted. To take advantage of this property for this application where it can actually replace a dichroic mirror. So how do you do it? You see, you use such a Brewster plate and put it as an intracavity element in this optically pumped laser. So let us see how it works. You have the gaseous medium which you have to pump, and you have to pump by another laser. Because as you know, such a gaseous medium cannot be pumped by a conventional light. You already know it, I am not going into any more detail. So this is that plate which you have put it at a Brewster. That means now your pump laser, you make it polarized. You know the output of the laser can be made, a laser can be made to produce polarized light. I'll just come to it in a while. But this pump laser actually emits polarized light. And you make it to emit S polarized light. That is the polarization which is perpendicular to the incident plane. So incident plane is here. This light shines onto this Brewster plate, and this is the normal to this Brewster plate. So the plane of this paper is the plane of incidence. So the polarization is perpendicular to this plate. So now you know that the S polarization can be both, this is Brewster angle, theta b, and this is S polarization. So it can be, this is the reflectivity. It can be both reflected as well as transmitted. So this polarization part will be reflected and the other part will be transmitted. It will just get out, escape, don't bother. Now the part which is reflected, it will travel through the active media and therefore it will pump it. I'm not going into the detail of pumping. So this laser operates at lambda 1 and it pumps it at that wavelength, the pump level, and eventually the gain occurs between the lasing transition and the lasing transition occurs at a different wavelength, lambda 2. Lambda 2 is of course more than lambda 1. We know this. So then the gain has been created at this wavelength. So first there will be spontaneous emission. And stimulated emission will be seeded by that spontaneous emission. Not spontaneous emission will give out light of random polarization. So the light that will be emitted by spontaneous emission will have random polarization. That means it will have both P and S component. Now, stimulated emission, which is triggered by this random light, also initially would produce light at that random polarization. That means this will have both the polarization, that is the S polarization. So stimulated emission, which is triggered by this randomly polarized light, will also in the beginning produce light with random polarization. That means it will have both the S polarization as well as P polarization. Now, as this light shines onto this Brewster plate at Brewster angle, therefore the S polarization, a part will be reflected and rest will be transmitted, while the P polarization will be totally transmitted because it cannot undergo any reflection at the Brewster angle. And this light, when it returns back to after experiencing reflection on this output mirror, when it returns back to this Brewster plate, again part of this S polarized light will be reflected. However, the P polarized light will be totally transmitted. So soon, the light that will build up inside the cavity will be enriched in P polarization. And in no time, S polarization will practically disappear because the stimulated emission rate is proportional to the number of photons present and on its polarization. Therefore, this will eventually lays on P polarized light and S polarized light will simply disappear. Such is the power of stimulated emission. Actually, there would be hardly any loss of power on S polarization. So this is how this Brewster plate works, and it can actually replace a dichroic mirror, and its optical damage threshold is very high because it hasn't got any dielectric coating like dichroic mirror, which has special dielectric coating. All right, so having studied the various way a laser can be optically pumped, both pulsed and continuous laser, let us now turn our attention to electrical pumping. So we next study the pumping of a laser, both continuous and pulsed, electrically. See, in the operation of lasers, the primary source of energy is usually electrical. And this is true for almost all the lasers that operate today. Now, while optically pumping a laser, regardless of whether by conventional source, that is a flash lamp or an arc lamp or a laser, the input energy drawn is first consumed to generate photons that would eventually pump them. This intermediate step invariably brings down the wall plug efficiency of the laser. Because you see, if you have a laser, this is the gaseous, this is the medium, lasing medium. which we'll have to pump optically. That means with light. You produce this light by, say, a flash lamp or an arc lamp. Flash or arc lamp, or even by another laser. So, how they produce this light? As you know, it draws electrical power from the line, and you actually you use a gas, put an electrical discharge, and this electrical energy then is converted into light energy, and then you pump this lasing medium by that. However, this intermediate step invariably brings down the wall plug efficiency of the laser. For example, if the flash lamp converts 50% of the electrical energy into optical energy and then converts 10% of the flash lamp light into coherent light, then wall plug efficiency is clearly 5%. That means what it says is that, suppose, let us assume that this laser gives out an optical power 1 watt, and we draw for this an electrical power which is 100 watt. Electrical power. And this, from this 100 watt electrical power, the flash lamp produces 50 watt light. So this is actually wastage. So if we can remove this intermediate step and pump it directly, this lasing medium, by this electrical power, this intermediate step is essentially wasting energy. That's what we say here. This intermediate step invariably brings down the wall plug efficiency of the laser. If the laser can instead be pumped directly by an electrical energy drawn from the line, then the intermediate step is dispensed with. This will cause a major boost to the energy conversion ability of the laser. So why should a laser be pumped by a flash lamp or another laser in the first place? Well, there are some limitations of electrical pumping. What are they? You see, electrical pumping basically relies on the transfer of the electron's kinetic energy into the lasing medium through collisions with its constituents, atoms, molecules, or ions. To understand this, let us once again take a look into the operation of a fluorescent light source. How it works? In a fluorescent light source, you have a discharge tube. You apply voltage to the tube, and there will be inevitably some electrons, stray electrons will be present, which will experience a force that is given by the product of the electron's charge and the applied electric field. Applied electric field is basically the voltage that is applied divided by the applied electric field is basically the voltage divided by the spacing between these two electrons. So the stray electron would then move towards the positive electrode because of this force, with an acceleration which is given by the force by the mass of the electron. Of course, there will be equal number of positive charges also present here, stray charges, but because stray charge, the positive charge will have much higher mass compared to the electron, so its acceleration will be much less, and therefore we don't consider that. And as the electron moves, it actually acquires velocity, and thus it acquires kinetic energy. The electron then collides with this kinetic energy, then collides with a neutral species, which can be light emitting species, which is present here, which can be an atom, molecule, or even an ion, and transfers part of this kinetic energy as the internal energy of the atom. The atom gets electronically excited. So the atom is initially the atom will be in the ground state, and after colliding with the electron, it will climb up to the excited state, and from there it will make a transition to the ground state and light will be emitted. So this is how the electrical energy is translated into light energy. First, the electrical energy gets converted as the kinetic energy of the electron. Then through such collision, the electron's kinetic energy is transferred as internal energy of the light emitting species, and then this internal energy eventually is realized as light energy. Now you can see, for this then, you need a collisional environment. Electron must be able to collide with atom, molecules, or ions. So this is impractical for liquid or solid medium. Electrical pumping is thus not viable for liquid and solid state lasers. The only exception is, of course, semiconductor lasers. We will know more about this when we study semiconductor laser in detail in some of the later classes. Now, the ability of a gaseous medium, on the other hand, to present a collisional environment makes a glass laser most suitable for electrical pumping of both continuously working as well as pulsed operation. So now you know that why to pump certain laser, basically liquid and solid state laser, electrical pumping will not work. That's why you need that intermediate state. That is where you convert electrical energy into light energy, then use that light energy to optically pump the solid and liquid state lasers. So, okay, so how do we electrically pump a gas laser in the continuous mode? So electrical pumping will not work for solid state or liquid lasers. So how do you pump a gas laser electrically? So the experimental schematic is almost same employed for operating an arc lamp, except that the discharge sustains here as a glow discharge. In an arc lamp, the discharge is sustained. It discharges a filamentary nature. It is an arc discharge. While here, the discharge actually fills the entire volume, enclosed volume that is in this enclosure. The underlying physics of conversion of electrical energy into light remains same as that of fluorescent tube light. We just described this. Basically, inelastic collision between energized electrons, which acquires kinetic energy in the discharge, and gaseous atoms, molecules, results in creation of population inversion between the desired energy levels. In case of fluorescent tube, you just create population, excite some of the ground state atom to the excited state. You need not attain population inversion because spontaneous emission will automatically occur and it doesn't require a population inverted state, and so light will be produced in case of a fluorescent tube. But if you have to make a laser, then you have to create population inversion. So you have to accordingly choose the energy levels. So you basically pump it here. The electron, after colliding with this light emitting species, will pump it to the pump level, then from there it will quickly relax to the upper laser level. This is the lower laser level, and the lasing emission will occur between this when you create a population inversion between these two. Now, under condition of CW pumping, the power supply also continuously feed. Only then it will work in continuous mode. When this gain medium when this placed inside a cavity, this is the cavity, it comprises of a partially transmitting mirror and the fully reflective mirror. One of the mirror, of course, has to be concave. Coherent light emerges as a continuous, coherent photons emerges as a continuous, coherent photons emerges as a continuous beam of light. To ensure glow discharge, operating pressure is kept low. Why operating pressure is kept low? First of all, why glow discharge is required? Because, say, if you will have an arc discharge, like an arc lamp, this is the electrode, and you have an arc discharge. That is where the current flows through a very narrow cross section. Then the light emitting species, which is lying outside this region, will not be able to collide with electrons, because electrons will be only there, confined into the region of discharge. So if you have to involve all these light emitting species, the discharge must fill the entire volume, entire enclosed volume. So the discharge has to be a glow discharge, not an arc discharge. Now if you increase the operating pressure, then the discharges tend to be restricted and it will actually grow into an arc. Why? Because you see, as you know, that there will be in the gaseous volume, there will be only some stray charges. But stray charges are not distributed uniformly. In some region, stray charge density may be more, as in here, compared to the other regions of this. So then, number of electrons will be more here. So the chance that more current will flow through this region also will be more, because initially the stray charge density is more. And if more current is flowing through this region, so chance that more electron will be created will also be more here. So once more current tends to flow across the region, it will continue to be a regenerative, more and more current will flow until and unless this instability actually diffuses into the rest of the volume. So this will work for a low pressure. The instability will diffuse into the rest of the volume, because at low pressure the mean free path of the electron will be more. So it will actually allow the instability to diffuse and be shared with the rest of the volume. However, if you increase the pressure, then the electron's mean free path will be very small, very short. And so this instability will stay localized, and eventually this will tend to, discharge will tend to be restricted only across a narrow region, culminating into a filamentary kind of discharge. If you would reduce the pressure at a low pressure only, you will be able to fill the interval. So that is why, to ensure glow discharge, operating pressure is kept low. At high pressure, the instability, if it grows, that is inevitable. There may be some instability, local instability, which will not be able to diffuse into the rest of the volume if the pressure is high. And so, for operating a continuous laser, it cannot be operated at a higher pressure. if you have to get a glow discharge, and glow discharge is very essential so that all the light emitting species participate in the process of lasing. And often a surrogate gas is also mixed to enhance the pumping efficiency. For example, for a helium neon laser, the light emitting species is helium. Light emitting species is neon, but helium is added with it to increase the pumping efficiency. Or for that matter, for the CO2 laser, the light emitting species is of course CO2 molecule, but nitrogen and helium is also added at very large quantity to enhance the efficiency of pumping and to enhance the operating efficiency of laser. These will be discussed in detail when we study the individual lasers like helium neon laser or carbon dioxide laser in more detail in some of the future lectures. So now let us come to electrical pumping of a pulsed gas laser. Now, we know that the low operating pressure of CW laser limits the maximum achievable power. See, if you have to increase the power, there has to be more number of light emitting species. So at low pressure, the density of light emitting species is low. So to increase the pressure, you will have to increase the density of light emitting species. So if you do not want to increase the density, the pressure, then what would be the other way that you can increase the pressure? You can of course increase the length of the activity to increase the output power. You can increase the length. But as increasing the length beyond the point is impractical. Output power is therefore increased by increasing gas pressure. Why impractical? Suppose you may have a typical length of the discharge to be say 1 meter. You can increase it to say 2 meter or 3 meter, but you cannot increase it to tens of meters. This is impractical. But you can easily increase the pressure. If the laser is operating at the 10 torque pressure, you can make it say 100 torque pressure. But there are a lot of hurdles if you increase the pressure. What are they? The challenges of high pressure operation. At high pressure, as you have seen, pulsed operation as CW in pulsed operation is mandatory, as continuous operation as obtaining glow discharge in continuous operation is not possible. And then there is another serious problem. Suppose this for longitudinal discharge, suppose it breaks, you have to apply a voltage to break this gap. This is called breakdown voltage. So if you operate at say 10 torque pressure, typical operating pressure of a CW laser, low pressure CW laser, say breaks at a voltage of 10 kV. That means if you apply 10 kV, then this gap will break. This is ground and you apply 10 kV. This gap may break. Now if you increase the pressure to say 100 torque, the breakdown voltage may be 100 kV. Now generating and applying 100 kV is very difficult to maintain such high voltage. There are many other associated problems. And if you increase the pressure further, breakdown voltage will be enormously high. So what is the solution? Solution is transverse discharge between specially contour electrodes. As you can see here, in this case, the electrodes have been placed transversely. And the electrodes are actually very well profiled, because if there is any sharp edges on the electrode, at that region field will be enhanced. So electron will experience more force there, and therefore there will be again a local instability. That is why the electrodes are very well controlled, well specially controlled. They are called uniform field electrode. That means the field over the entire length of the electrode will remain uniform. And then rapid discharge to prevent glow to arc transition. Even if a discharge begins at glow mode, within glow mode means it fills the entire volume within a short time, which is inversely proportional to the pressure. Higher is the pressure, this glow to arc transition time is shorter. So depending on the pressure, you will have to ensure that the discharge, entire energy is pumped within the discharge within the glow to arc transition time. Otherwise, the discharge will arc and your lasing will perform with very poor efficiency if it at all lases. So then how we will make it work? Of course, you will charge a condenser first to the appropriate voltage. When the condenser is charged to the required voltage, high voltage, high current switch closes, and this will allow the condenser to discharge its energy into the inter-electrode volume. And you have to take a lot of special care to ensure that condenser discharges within a time which is less than glow to arc transition time. So the laser performs very efficiently, the discharge stays as a glow discharge, so that the entire volume and all the light emitting species present there, they can participate in the lasing process. The best example of pulsed gas laser is carbon dioxide laser, which can easily emit tens of megawatt of power over several hundreds of nanoseconds, compared to just tens of watt for a conventional CWCO2 laser. But this, I'm only giving you some very brief exposure to this. You will learn much more on this when you study a carbon dioxide laser in detail in some of the future classes. Okay, I will end my lecture today.